Elimination method to solve systems of equations. So systems of equations have two variables and two equations to solve for. If we have x plus y equals 5 and x minus y equals 3, kind of like we did in elementary school, we could add these up and down. And if we add them up and down, 1x plus 1x is 2x. A positive 1y plus a negative 1y cancels out. Additive inverses will cancel. And 5 plus 3 is 8. So in this case, the y's are eliminated, and we're left with the equation 2x equals 8. Well, that's easy to solve. We just divide both sides by 2, and x equals 4. Once we have x equals 4, we can go back, substitute into one of our original equations, and get a y value of 1. So our solution would be the ordered pair 4, 1. Well, how did this really work? Well, it worked because we had opposite signs, and we had the same coefficient, in this case a positive 1 and a negative 1, that when we added them together, they dropped out. So that eliminating of y is what allowed this to work so easily, because we had opposite signs with the same coefficient. So when we have that, elimination is a great way to solve systems of equations. It can be a whole lot quicker than graphing, and sometimes even quicker than substitution. So let's look at a new problem. We have c and d in this one. Negative 5c plus 3d equals negative 16, and negative 10c plus d equals negative 22. And if we're looking to eliminate the c values, I have the same signs. They're both negative, so I'm going to want to multiply one of these equations by negative 1 to make them have opposite signs. And if I think about my least common multiples for 5 and 10, counting by 5s, 5, 10, 15, 20, counting by 10s, 10, 20, 30, the least common multiple would be 10. So I can take that top equation and multiply by negative 2. If I take that top equation, negative 5 times by negative 2 is going to give me positive 10c. I just have to also multiply the rest of the equation by negative 2 as well. 3d times negative 2 is negative 6d. Negative 16 times negative 2 is 32. Now what I've made is my c's have the opposite sign and same coefficient. So when I add these two equations together, the c's will eliminate, and d plus negative 6d is negative 5d. Negative 22 plus 32 is 10. Divide both sides by negative 5, and I've solved for d. Once I've solved for d, I can just go back to any of my original equations. I can finish solving my problem for c, put my d value in of negative 2, add 2 to each side, divide by negative 10. Then when it comes to write my ordered pair, I still want to do it alphabetically like we do with x, y. I'm going to do c comma d, so 2 comma negative 2 for my ordered pair. I can always go back and substitute in and make sure that these 2 points work in both the original equations, just to verify that they are good points. So here's our steps. Step 1, we want to arrange the 2 equations in standard form. You want ax plus by equals c, so that all your x values line up, your y values line up, your constants line up. Step 2, if necessary, multiply one or both equations by appropriate numbers so that the coefficients of x or y are opposites of each other. Step 3 is to add the 2 equations to get one equation with only one variable. Step 4 would be to solve for the remaining variable. Step 5, we can use substituting the value of the variable into one of the equations to solve for the other variable. Use the substitution, basically go back, get the other variable. And we can always check, make sure our point works in both equations. And we always want to write our solution as an ordered pair. Well, let's look at one where we have to multiply both equations. So let's say we wanted to eliminate the y's in this case. Well, we have opposite signs. I have a subtract and an add, or a negative and a positive. Least common multiple for 3 and 2 would be 6. So if I want to get this to be a negative 6, I take that whole top equation, multiply by negative 2, giving me 2x minus 6y equals negative 14. And to get this 2y to become a positive 6y, I want to take that second equation and multiply by 3. Now make sure you multiply every term by 3. Some people will forget to multiply this term on the other side of the equal sign. 23 has to multiply by 3 to get 69. Then we can do our elimination, and if we pick the correct numbers, and we did, the y's cancel out. 2x plus 9x is 11x. Negative 14 plus 69 is 55. Solve for x, divide both sides by 11. X is 5. And then once we have x is 5, the steps are the same as we did with substitution method. We can go through, substitute back in, and get our y of 4, writing the ordered pair 5, 4. All right, you guys pause the video here and see if you can solve this system of equations. All right, welcome back. These are not in standard form, so we need to rearrange, get these in standard form, get them in ax plus by equals c. So we want to rearrange the equations. Then we want to do elimination. I can either eliminate the x's, do it like a least common multiple of 6, or I could do elimination with the y's to a least common multiple of 15. I chose to eliminate the x's, so I took the top equation multiplied by -2. I took the bottom equation and multiplied by 3. This way I got my x's to be eliminated. Now, if you did the y's, don't panic. You will still end up with the same answer at the end. Your steps just look a little different at this point. So in this case, my x's cancel out, and then my y's, a 10y plus a negative 9y is y, and 4 plus 3 is 7. So I get y equals 7. Go back, substitute in, and I can get my x value. So once I get my x value of 11, I'm going to write the ordered pair 11, 7. So even though I found the 11 last, it is still the first number in the ordered pair, x, y. All right, we have 2x plus 4y equals 5 and 4x plus 8y equals -9. And if I try to get the x's or the y's to eliminate, I can take that top equation and multiply by -2. And when I multiply by -2, 2x times -2 is -4x. 4y times -2 is -8. 5 times -2 is -10. When I try to do elimination on these, both the x's and the y's cancel out, and I'm left with 0 equals -19. Well, that is a false statement. So what does this really mean if the variables drop out and give us a false statement? Well, if we were trying to graph the same equations, system of equations, we'd end up with parallel lines. So what this is showing algebraically with elimination is this false statement would indicate that the lines of the two equations would not intersect and therefore has no solution. So graphically it would show parallel lines. Algebraically it shows the variables dropping out and leaving a false statement. If I try to solve this equation by, let's say we try to get the y's to drop out, I could multiply the top equation by 4 to get 12y. And then to get the second equation, have a -12, I'd want to multiply by 3, and I get a -12y. Or if I try to get the x's to drop out, I would still multiply by 4 and 3, because in this case, the x's and y's both cancel out, and I'm left with 0 equals 0. So my variables dropped out, and I'm left with a true statement. So if I tried to graph this, if I'm trying to interpret what does it mean when my variables drop out and I get a true statement, what that means is graphically, if I were to put this on a coordinate plane, they would make the same line. So this is a true statement, therefore the equations are the same. It would make two lines that coincide with each other and produce an infinite amount of solutions. Every point that works on one line would also work on the other. And that should get you guys started on solving systems of equations with elimination. OUT spells out.